Shall we wrap this up? Okay. Our final is on Monday, which is the worst time to have a final for a class like this, right? Because you don't have much turnaround time. On Monday, 11 a.m. to 1:45, and I will stop the test at 1:45 just because other, people might have other tests they have to get to, things like that. So there won't be any extended time. That's when the mini exam thing is due, right? That's when that's due. And in terms of the what you can have for that test, you can have all the formula sheets, right? There's a ton of them, yes? And I'm feeling especially nice today. So this test is going to be open note test. Completely open note. So you can use all your notes. What you cannot use is the review exam thing you're going to turn into me. You can't use that, okay? So you can have problems worked out, right? But what you turn into me that day needs to be turned at the beginning of class, yes? I'll let you, how about you choose one or the other? If you want to have the textbook, you can have the textbook, but you can't have your notes. If you want your notes, you can have your notes, but you can't have the textbook. Yeah, so, yeah? Are there any restrictions on that? No, not really. Really, what this comes down to is when you see the problem, are you going to be able to figure out what you need to do, right? That's it. And hopefully from there you can execute the problem. I will tell you on the actual exam, I will tell you whether or not I want you to take that problem all the way to the end, or whether or not I just want you to set up the integral. And a lot of times in class, right, I was like, let's get it to here, and then we're like, yeah, forget it, we'll go to the computer for that. I'll let you know on the test. On the take home, right, all of them you're supposed to just take it all the way, right? But on your test, I might not do that. Which might mean, that might be good, might be bad, might mean now I can give you more problems because you don't have to take them all the way, right? All right, any questions over the exam? No? Okay, so turn in that test that same day, and here we go. So we're going to wrap up 13.8. This was Stokes' theorem. And in talking with a few of you in here, before we use Stokes', I just want to kind of remind you that when we were back in a previous section, when we were in R2, we had this thing called Green's theorem. This is just make sure you make this connection, Green's theorem. What Green's theorem said was that if you're doing a line integral along a closed curve of f dot dr, right, which is basically the work integral. This is trying to find work. If you're trying to do the work integral, then if you're in two-dimensional space, if your curve C, right, whatever your C is, if your curve encloses a region, which we could call this region in here R, let's say, Green's theorem allowed you to turn this line integral into the double integral. Anyone remember what it is? The line integral over C is the double integral over, in this case, R. I'm using R. Remember what it was? So that's in R3. That's in R3. Yeah. What's Green's theorem say? It's partial of, yeah, it was partial Q with respect to y, partial P with respect to x dA. That's Green's theorem. That's Green's theorem. Where P, what are P and Q here? P and Q are the components of the vector field, right? Make sure you talk to me after class about the final. There's some important information I need to give you. All right. So your field was P and Q. So this is exactly what Stokes' theorem is doing, but Stokes is in three-dimensional space instead of two-dimensional space. With Stokes, what we're doing is we're trying to do the line integral work, right, over some curve C of f dot dr. That's a vector on R, sorry. Right? So we're trying to do that, but now we're in three-dimensional space. And so our curve is in three-dimensional space, whatever it is. That curve C, what we can do is we can convert this into a, what does Stokes' theorem say? We can convert this into a
double integral over S.
Over S, so surface integral, right? A surface integral of what though? Curl of, oh gosh, I can't do curl today. Curl of f ds. Curl f ds. And here, what is S? S is the surface enclosed by that curve, right? In two-dimensional space, do you all agree that there's only one R possible here? I mean, R is R, right? It's that region there. But with Stokes' theorem, this surface S can be any surface that has this as a boundary. Any surface. Now, the one that's most time natural is if it's like a plane, we could use that, but not every surface here has to be flat. This surface S can be any surface that is just that has that as the boundary. So what I'm telling you is that Green's theorem is the two-dimensional case of Stokes' theorem. And you can convince yourself of that by thinking about this field. If you were to use this in Stokes, as Stokes instead, and extend yourself out into three-dimensional space, your R would be 0, wouldn't it? And then if you find the curl of this field, guess what? It comes out to be this. That's your curl. So that's where the Greens comes from. Okay, with that said, let's go ahead and continue on with the last example out of this section, which is to try and figure out what the work done is by moving along the curve, which is the intersection of this plane and this cylinder through this vector field. So we've got a plane, right? That's the plane x plus y plus z equals 1. And then we've got some cylinder. That cylinder has a radius of what? 3. And then they hit each other, right? They intersect each other at some curve. Depending on the slant of that plane, we're going to get some curve there like that, right? That's our C. And I'm going to tell you, even though I didn't put it in this problem, we're going to orient C so that it's clockwise when you look from the top. So if you're looking down from the z-axis, it's clockwise. Wait, did I say clockwise? Sorry, counterclockwise. Sorry, counterclockwise. Looking from the top, it's counterclockwise. All right, good? So what I'd like to do to really show you the power of this theorem is I would like to do this without Stokes' theorem first. And we're not going to do the whole thing. We're going to get the integral set up, and then we're going to say, okay, let's look at what that's going to take. So let's see if we remember how to do work. We talked about this last class. How do we do work? We do F, right? The field evaluated along the curve, right? And then dot that with the derivative of the curve. So to do this without Stokes, I'm going to do this. I need to find, I'm going to need to find this. Let me see. This right here is going to be the integral of the field evaluated along the curve, dotted with the derivative of the curve dt. And then our limits of integration will be a to b, whatever our restrictions on t, whatever the restrictions are for t. All right, well, I need to figure out what r is. I need to be able to draw the curve, right? So I've got to be able to draw that curve. So to draw this curve, r of t, this right here, I know that when I look at this curve from the top, it looks like a what from above? A circle in the xy plane of a radius 3. So to do that, I'm going to use some sine and cosine stuff, right? 3 cosine t, 3 sine t. And then the z component is the up and down. And if it has to live on the plane, right, the red thing lives on the plane, then it has to satisfy the plane equation. And so what should I do?
Set x and y equals to 0?
No, all of these, every point along this curve, the x and y coordinate are going to be dictated by this, right? But what about the z, the height? That's going to be, that would be down here. You solve for z. Right, this is the plane equation, right?
Yeah.
If I solve that for z, that tells me the relationship between z, x, and y. If I solve this for z, what do I get? 1 minus x minus y. And then do I know what x and y are? Yeah, that's x, that's y.
Okay.
So my z coordinate is going to be 1 minus 3 cosine t minus 3 sine t. That is the vector function which draws that red curve, which is the intersection of the plane and the cylinder. Question? No? Okay? Now I'm going to have to take that vector function and evaluate the field on that vector function, but then dot it with the derivative. So let me get the derivative now. So the derivative of this, because I'm going to need it. Oh, by the way, what's the restriction on t? I didn't put it here. T is between what? 0 to 2 pi. Because remember, we're drawing the circle, right? So 0 to 2 pi for t. All right, derivative. We've got negative 3 sine t. We've got 3 cosine t. And then we've got 3 sine t minus 3 cosine t. So just differentiating each of these one by one, right? That's my derivative. All right, fun stuff now, right? We need to set up this integral. I'm going to squeeze this in. Squeeze it in right here. All right, so I need to do the integral from 0 to 2 pi. Okay, the vector field, which means it's going to be a vector, right? Evaluated r of t. So I've got to take this field right here, and I've got to replace x with 3 cosine t, and y with that, and z with shit, right? Okay, so x squared, what's x squared for me? 9 cosine squared t, that's x squared, times z, 1 minus 3 cosine t minus 3 sine t. Okay, that is just that part, right? Then I have comma. Now I have this one, which is, let's see, x, which is 3 cosine t. And then 9 sine squared t, that's squaring the y, right? And then z squared, which is 1 minus 3 cosine t minus 3 sine t, but all of that squared. Okay, that's just the field evaluated along that curve, right? I need to dot that with what? Dot this with that. Sound fun? Doesn't sound fun to me either. So I had the computer do it for me. Like, I didn't have the computer do it. I typed it in the computer myself. So here's what I did, just so you can, I wanted to show y'all how this program can work. I can define a field. I define the field right here, x squared z, x times y squared z squared. That's my field. And then I defined what x was, what y was, and what z was, right? I defined. And then what I did is said, okay, give me that field evaluated at the x, y, and z I just gave you. and it went ahead and gave that to me. So this right here, that right there is, I know this is hard to read, but that's this right here, okay? So I said, all right, great. And then I said, go ahead and expand just means make it look nicer. Take that field that I just defined at XYZ, and this is the notation for the dot product in this program. So dot. And I want you to dot it with what? The derivative of the x with respect to t, the derivative of the y with respect to t, the derivative of the z with respect to t. Go ahead and dot that out. And it dotted it for me, okay? And then I called that dot product A. I just picked a letter. And then the next thing I said is go ahead and integrate A from 0 to 2 pi. And I got an answer of 81 pi over 2. But just to give you an idea, this is the thing that we would have to, this is the thing that we would have had to have integrated right here. What you see right there is what we would have integrated. And can you imagine that integration? Could you do this? Yeah, okay, that'd be easy. Okay, so you can do that, right? Power reducing, you could do that. This one, okay, you peel a cosine off and you could do that one. That one you could do. Here you got some cosines mixed with sines. And so you would, basic U substitution should work here, basic U substitution here, power reducing here, basic U substitution, basic U substitution. Whoa, no, these are both squared. Yeah, I could do some power reducing there and then peel off one. So it's doable, right? But like an hour later, we have the answer, right? So now what we'd like to do is approach this from Stokes. From Stokes' theorem, Stokes' perspective. So now with Stokes. Okay, so with Stokes, what I'm going to do is I'm going to realize that this curve is the boundary of a surface. And that surface there, I'm going to call that S. And I could pick any surface that has that boundary, right? Any surface, as long as that, you know. Think of it like this is the outer ring of a drum. You have a membrane in between, and you could push that drum, and it would, you know, the outer edge would stay there, right? You push down, it would deform the inner shape. That would be a different surface. We could do any surface we want, as long as that outer edge stays the same. But for us, the one that makes the most sense is if we just do a flat plane through there, right? Like a flat, nice little disk. That's what I'm going to choose for S, all right? Okay, so that's what S is going to be. When I do this, I'm going to have to do the curl of F, right? For my new integral, we have this. This is Stokes's of curl of F dot ds, right? That's what we're going to do. So I need to find the curl of F. We may as well, right? So to do the curl of F, we need to do del crossed F, right? That's the curl. So del is the partial operator. And we're going to cross that with our field. All right, let's see what this cross product looks like. Well, I don't like that. Okay, so here, what's that? So here to here we get 0, right? And then here to here we also get 0. So we get a 0 there. And then when we cover up the middle, go here to here, 0 minus x squared. But it's the middle one, so just x squared. And then cover this one up. Y squared, take away nothing, right? So just y squared. Okay, that's my curl. That's my curl. Now remember, at this point, I appreciate y'all coming today. Y'all have a great rest of your semester. You doing good?
Yeah, try.
Okay. No, you don't have to explain. I just like to do that every single time someone walks in. For me, it's fun. All right, so we are going to do this, right? We're going to do this. So now what we want to do is we want to take a step back and get our sheet out that has surface integrals, the one that was colored that has the numbers on it. Right, we want to do surface integral. And we just want to remember that really, now at this point, this is actually the field we're talking about. The curl of f is the new field, right? And when we look at this, we look at our field. Here's our new field that we're going to be working with, right? And we look at our surface over here, S. The first thing that I'm going to ask myself is, can I look at S as being a function of two variables? In other words, can I look at the domain of that as being down on the xy plane or projected to the side? Is it easy for me to define this surface as a function of two variables?
Yes.
Yes. Right? What is the equation of this plane? Z equals 1 minus x minus y, right?
Yeah.
Like that is some function of two variables, x and y. Right? My surface is. So what formula is it that I'm looking at then? A, B, C, D, E, F, G. Which one are we going? F? Do you all agree? F is how we do surface integral of a field over S if your function is a function of x and y, which it is. Okay? So I'm going to use formula F for this. So formula F is going to be, oh, what about our normal vectors? For that plane, our normal vectors are pointed right up like this. If we're going to use this formula, right? Normals are pointed up. That's the formula we're going to use. Now, this is not a closed surface, right? So we're going to use the orientation of up for our answer. If we use the orientation of down, then we'll get the same answer, just opposite sign, right? So let's do it. Double integral over d. Where's our domain in this picture? In the xy plane, down on the ground, right? And that's just a what? Circle down there? That's d down there? Yeah, we'll go to polar for sure. Double integral over d. Okay. I'm following formula F. Negative p. What's p for us? 0, right? This is p, this is q, this is r. So 0, negative 0, the partial doesn't matter, does it? Okay, minus q. What's q? X squared. Let me put that there. Do you want me to write these in? I'll write them in. Negative 0, that's p. We never got our partials. I'll go ahead and get partials over here. Partial g, right? Partial g with respect to x was negative 1. Partial g with respect to y was negative 1. So those are my two partials over here that I need for my formula here. So that's 0, negative 0, partial g with respect to x would have been negative 1, right? And then I have minus q, which is x squared, and then partial of g with respect to y, which is negative 1, and then plus y squared. All of that dA. dA. Yeah, and that just turns out to be the double integral over d of x squared plus y squared dA. And fortunately for us, D, right, is a polar region on the ground, right? So when we convert to polar here, we're going to let x be, right, so we're going to go polar. So x is r theta, y is r sine, wait, no. X is r cosine theta, and y is r sine theta. Theta is between 0 and 2 pi. R is between
0 and 3.
0 and 3, right? Because the radius of the cylinder is 3. Okay, so we can do this. It's going to go 0 to order doesn't matter. Okay, x squared plus y squared, when you go to polar, is r squared. But then we also have the r from going to polar. So r cubed, dr d theta. I argue that that's a much better integral than the one we had just a second ago that I put up on the board. Yes? Let's do this integral. We haven't done one of these in a while. Inner integral first, this one. The antiderivative of r to the third, 1/4 r to the fourth, evaluated from 0 to 3. And then when I'm done with that, I'm going to have to do d theta, right? This should be pretty straightforward. 3 goes in here. 3 to the 4th power is 81. 81 over 4, right? So we have 81 over 4. Oh, come on. 81 over 4. But we still need to integrate that from 0 to 2 pi d theta, right? And the antiderivative of 81 over 4, just 81 over 4 theta evaluated from 0 to 2 pi. And then plug in your 2 pi. When 2 pi goes in there, you can reduce the fraction, right? And you just get 81 pi over 2, and then when you plug in 0, it goes away. And that's the same answer that the computer got a second ago. Much easier, right? Much, much easier. So that's it. We'll talk about the final in a second, in a little while. I want to kind of take a step back, because I've told you all, I've been asked, can you use Stokes' theorem now from here on out? You know, like anytime you see like a work integral, can you use Stokes? Well, yes, maybe. The only time you can ever use Stokes to do a work integral is if your curve is, well, it could be in 2D, it has to be closed. Your curve has to be closed. That way it's the boundary of a surface. If it's not closed, then you can't use Stokes. So on final exams, what I do is if I want you to do a work integral, then I'm going to give you a curve that's not closed, and that will force you to do the work integral. There won't be a way around it. But if I close the curve, then you start going, oh, well, wait a minute, maybe this is greens. If you're in two-dimensional space, you'll say, I'm going to use greens. Or if you're in three-dimensional space, you'll say, I'm going to use Stokes, right? So, but we'll talk more about this, all right? All right, next thing is the last section, all right? So that's it for Stokes. So the last section in this book, right, it's not just the chapter, this is the book. It's called the divergence theorem. And just like Stokes' theorem, the divergence theorem gives us a way to do something that was harder before. We can do it in a much easier fashion. Well, it's not always going to be the case that it's easier, but it gives us another tool that a lot of times does make it easier. But there's some stipulations. It's not, you can't always use it, only certain times. So let me see, where is it? Did I close it? There we go. So this is the divergence theorem. So let E be a simple solid. So it's a solid three-dimensional shape, right? And S be the boundary surface. So a basketball, right? Solid, well, basketball is not solid. Bowling ball, a solid ball, right? That's E. The surface of it is S. So if I have some solid, three-dimensional space, doesn't matter what the shape is. I'm not saying that this is a box or anything, just some solid. Okay, the solid is E, right? But the boundary of it, the surface around it, is S, right? So all this, the back side, all the surface together, that's S. Says we also have to talk about the normals. Let S have positive orientation. So the S has the normals pointing away from the solid. Okay? The surface is closed, right? So it's going to have an inside and an outside. Positive orientation means the normals are pointed away. Let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. That just means that assume that there's a field, like this object lives in a field, and that field is well behaved, that we don't have some crazy stuff happening where the field fails to be defined or something like that, somewhere around this region. Then we have this very nice divergence theorem. This is what? What is that? Flux. It's flux, right? flux. The flux through the surface is equal to what? The triple integral over E, the solid, of the divergence of the field with respect to volume. If I put Stokes's below this is Stokes's theorem. That's Stokes's, right? First thing I want to point out is that Stokes allowed us to take a work integral over a closed curve and then turn it to a double integral over a surface, right? Of the curl of that field. Not the field, the curl of the field. The divergence theorem says, okay, well, if you ever have a flux integral, right, where you have a surface integral, there's a field, ds, that you can do that by evaluating the triple integral over the solid E that it encloses, and you use the div of the field. So the Stokes uses the curl, and the divergence theorem uses the divergence, which is why we call it divergence theorem. I guess this one could be called the curl theorem, right? Curl theorem, divergence, but curious. Do y'all see this? It's not going to come up in your homework or anything like that. But do y'all see this? Do y'all agree that the curl of F is just some field? Right? Could I use this theorem now? Could I? You sure? Think about it.
Well, it's another field.
It's another field, yes. So you basically have this, yes.
I was looking at
Yes, think about it. What is the condition on this surface? That it what? That it encloses a solid, right? Does this surface enclose a solid? Where did that surface come from? The closed curve. The closed curve was what? A curve, and then you had a surface between them. Is that surface closed? It shouldn't be closed, should it? Like if you draw me a curve in three-dimensional space and then think about a surface between there, is that a closed surface? Not generally, right? Would it be possible to even draw a surface that's closed that has a curve as a boundary? Could you? I mean, think about it. If I gave you a curve, right, in three-dimensional space, can you draw me a surface in between that has that as a boundary, okay? So the curve is the boundary, but the surface, is it possible to draw a closed surface that way? A donut? Okay, so you're saying like do like a torus kind of, like the curve goes